This is a set of random numbers between 0 and 100, purely random, generated, and the purpose of this is to look at how the average and the standard deviation become the average and the standard deviation. Most people don't get to see this because they get a data set that already has all the numbers in it. But the purpose of this is to look at how long it takes the average to settle down and the standard deviation to settle down, regardless of the number of observations that you have. Since this is random data, it's going to bounce around as much as possible, but what we want to do is calculate the average and the standard deviation as each sample value enters the sample. So we want to calculate the average as each observation enters the sample. We'll do the first two because the average of the first one is just the average. So we want here the average equal to the first two observations, which will be C7 colon and C8. Then go back into the formula and we want to lock the C7 so we always stay with the 7, put a $sign in there. So we always stay with the 7 plus all the other numbers that are coming in. We copy this down to 50 observations. And what we want to look at is how does the average change as each one of these numbers comes in. We can look at this most easily by looking at a graph of the average as the values come in. We'll use the insert, and we want a scatter diagram, and we can connect it with lines, straight lines. We can change it later. Click in here and select data, add, and we'll put in a series name, average. And the X values are simply going to be the number of observation, and we'll start at 2 because we don't have an average in 1, and the Y values will be the averages of the numbers as they have come in. And this is a graph of how the average becomes the average. As we go in here and look down this list, which has a lot of decimals in it, once we get to about 40 observations, this stuff has basically stopped moving. The average is the same from 40 to 50. It doesn't move enough to make any difference. This is because we have a long chain of previous observations which are going to hold down the average, or the change in the average, as a new observation is added. For example, we have a 13 here at the number 16, and it changes the average from 15 to 16 by about 1, actually, or 2. If we go down here further, we get another number, say 51, and between 35 and 36, the average changes by 0.1, so that each additional observation makes less and less difference. And because these are random observations, purely random numbers uniformly distributed between 0 and 100, this is the absolute worst case for the average settling out. Most data sets will settle out much quicker because they don't have the possible range of these numbers. But this way, the average stops moving, and this is why a sample size of 2,000 is really irrelevant. Once we get past 50, in even the worst case, nothing's going to happen that's different. we can do this same thing for the standard deviation. And for this, we'll take the standard deviation of the first two. We have to have at least two observations for standard deviation, and this will be STDEV.S. This is the sample standard deviation, a divisor of n minus 1, and we do C7 to C8 again, and then change the formula so we lock the C7 position, put a $sign in front of that, and copy it down to the rest of the observations. Now, we'll make another graph with the observations in here, or we can put it on the same graph. Go back into the graph, right click, and we want to select data. And we want to add standard deviation as a name. The series X values are simply the 2 through 50 as before. The Y values are the standard deviation values. And we have another series on there. Now in this is one of the stranger things in statistics. The change in the average, the bounce in the values, the measure of the bounce in the values stops changing much faster than the average itself stops changing. This one, basically, once we get past, say, 20, 25, there is no difference in those numbers, so that as we go through here, anything past the 25th observation or the 30th observation is basically immaterial to the standard deviation. This is because once we have seen the difference that occur between observations, once we've seen that and it's big, then we've seen it already. If it happens again, it isn't that important. So that these two things are very important in statistics because we have sample sizes much bigger than 50, sometimes in the thousands, and in those cases, once you have 50 observations, nothing is going to change in the average and the standard deviation. So that sample size of 30 or 40 is enough for just about anything. And in fact, this is why you can get a poll number for an election for the entire United States from about 1,000 people, because it doesn't change. Once you have the average and the standard deviation, all you need to increase the accuracy is the sample size. And once you get past a certain sample size, nothing is going to change in the standard error of the mean.